Why should we and how can we best teach molarity to our high school chemistry students? I start off with giving you 3 examples of items that we can send off to a lab to be measured in terms of components inside these items. One of them is urine, another one is blood, and 3 is what we hopefully drink every day, and that's simply water, our tap water. We can determine the pH of our urine. Varies widely because it depends on our diet and the level of hydration. Measuring protein and glucose in milligrams per deciliter gives us a lot of information about our kidney function. The ketones in our urine are a telltale sign whether we're on a low-carb diet or maybe something more severe like a metabolic disorder, measured in millimoles per liter. It's good to evaluate whether there's some blood in our urine. You do not want to have blood in your urine. Bilirubin is a byproduct of the breakdown of our red blood cells. And leukocytes in cells per microliter, nitrite in milligrams per deciliter, are a telltale sign if you might have a urinary tract infection. So these are some 8 key measurements that can be taken from your urine, underscoring the importance of understanding concentration, including molarity. Second, bodily fluid that we can send off to a lab is our blood. Glucose is obviously a key item that we can measure, and it's a telltale sign if we may suffer from diabetes. Sodium, potassium, and chloride, measured in milliequivalents per liter, are key electrolytes. We need them. Calcium for our bones in millimoles per liter, magnesium for all kinds of cellular processes, including muscle function, in milligrams per deciliter. Urea, creatine, bilirubin, and carbon dioxide, measured in either micromoles per liter or millimoles per liter, are different kinds of waste products. I've shown you here 10 different components present in our blood. Obviously, many more items can be measured in our blood, but again, this is a second example that underscores the importance of understanding the concept of concentration. Depending on where you live, you may need to have enough disinfectants inside it so that there are no pathogens present. So one thing that's key to measure, maybe the pH, should be between 6.5 and 8.5, relatively wide range, and the levels of chlorine and bromine, reminiscent of also your pool, in milligrams per liter, which is basically parts per million. So I've just shown you 3 examples of items that we can send off to a lab to be tested in terms of the various components inside them: urine, blood, and tap water. This underscores the importance for students to understand concentration. But we can measure concentration in many different ways, whether it's parts per million or whether it's in molarity. I'm showing you here a titration setup because that's often how we think about molarity in the chemistry classroom. So molarity is defined as moles of solute per liter of solution. So I'm about to show you the activity that I did just last week with my students concerning molarity. In the bottom of these slides, there is a Pear Deck interactive bar. You can use it or you can ignore it. I've done this activity within Pear Deck so that I can get immediate feedback from my students. Alternatively, you just print out the slides and they can answer them using pen and paper, whatever you prefer. Again, go to the description in the link below to get your copy of these handouts with the key. This shows you the first slide of the student activity. It involves them creating a serial dilution involving 3 tubes at first, tube 1, tube 2, and tube 3. And we're going to pretend that 1 drop of blue food dye is simply the equivalent of 1 mole. Got to do a little bit of pretending here. And that 1 full plastic dropper is the equivalent of 100 milliliters. I know it's not the same, but it makes it a lot easier than measuring exactly 1 mole of something and 100 milliliters of something else. All right, tube 1 has that 1 drop of blue dye and in addition 5 full droppers of water. And the students can then measure what is the molarity in tube 1. Based on 1 drop being 1 mole and 1 full drop per being 100 milliliters. My student is showing you here how she took 1 dropper from tube 1, moved it to tube 2, and added another 4 droppers of water. What's the molarity inside tube 2? And how does that compare to tube 1? Should be more dilute, right? Now my student is showing you how she moved 1 dropper full from tube 2 and moved it to tube 3 and added another 4 full droppers of water to tube 3. How does the molarity of tube 3 compare to tube 2 and to tube 1? Here you can see the key to that activity. How does the molarity of tube 1, 2 molar, compare to tube 2, 0.4 molar, compared to tube 3, 0.08 molar? All the calculations are shown here at your convenience. But what's a molarity exercise without using the actual dilution formula? So they've used the molarity formula, moles per liter. The dilution formula involves MAVA, MBVB, or M1V1 equals M2V2. Let's check it out. So to practice with that dilution formula, they are receiving the following prompt. How much volume from tube 1 would you need to make a new solution that has the same concentration as tube 3? And this new solution needs to contain a total volume of 5 droppers. And I gave him this tiny test tube, which barely fits the total, further emphasizing how much water molecules like to be attracted to each other. And so you get that bulging meniscus at the top. And then they're asked, can you make this new solution after they've done their calculation directly in that little test tube from tube 1? And they can then compare whether they did it right by comparing their little test tube's color to tube number 3. By following the dilution formula, they should be able to calculate that they only need 0.2 droppers from tube 1, transfer it to the little test tube, and add another 4.8 droppers of water. Here you're seeing my student do exactly that. 0.2 droppers from tube 1, and then adding an additional 4.8 droppers of water, with the end result containing a small test tube, tube 4, that has the same concentration as tube number 3. All right, so this is a very brief and simple activity that allows students to practice the molarity of a solution, the dilution formula, and actually get a visual from that because you're playing with food dye. You don't like blue? Choose a different color. It's all up to you. What standards are we following here? Next Generation Science Standards and the New York Science Learning Standards, HSPS 1-5, collision theory and rates of reaction. Without understanding concentration, we can't then take it to the next step where we're going to talk about kinetics and reaction rate. But as I showed you in the beginning of the video, I think it's also really important to underscore the importance of understanding concentration when it comes to measuring different components that we deal with in our life, including our urine, our blood, and the water that we drink, among many, many other possible examples. Check out some other videos that make sense as either a starting point or a follow-up to this one. I have a video linked above about acids and bases, an explore before explain scenario. Stay tuned for an upcoming video on microtitrations that doesn't really use the following titration setup, but instead a well played on a balance. Bedankt voor het kijken. Thank you for watching. See you in the next video en tot ziens.